All right, welcome to Math 400, it's Calculus 1. And in this video, we're going to be looking at a handout that I sent out called Am I Ready for Calculus? Now, this is all review, and just to give you an idea of how this class is typically taught and things I've done differently in the past when I've taught this course. We in our textbook are covering up through chapter 5. That's where Calculus 1 ends. And if you look in your textbook, chapter 1 is a review chapter. It's covering only material that you would have covered in the prerequisite courses you should have taken before getting here. You know, algebra, pre-calculus, geometry, trigonometry, all that kind of stuff. I have taught this course, the first time I taught this course, I took the time to go through chapter 1 and cover all of that review material. And what I found when I did that was it ate up a lot of time. And this class is a lot of material that we need to cover. And it ended up not really being worth all the time we spent on chapter 1. So the second time I taught this course, I skipped chapter 1 completely and just jumped right into chapter 2. That gave us more time to cover the course material, but there were several students who said that they would have benefited from spending a little bit of time at least on that review material. So I have since created this handout, which I've been using since then, to hit on some of those important review topics before launching into any actual calculus. Now, this handout is not something I'm collecting. It's something that I just want you to look over and try and work out all the problems on your own. But if you've had a chance to look at it, what I want to do is run through the solutions of a selection of problems on here. We're not going to go through each and every single problem. We're instead just looking at certain specific problems. So this has been split up into 5 sections. We have algebra, geometry, and what we call analytic geometry. We have a section on functions, which does fall under the category of algebra, but it's really a bigger subject than that. Trigonometry, and then something that we call modeling or mathematical modeling. So we're going to take a little bit of time to look at each one of these sections. I do have an answer key in the back, so let me actually set that aside so we can verify our answers. Put that up here. Okay, so let's take a look at some of these algebra problems first. You'll notice the majority of these problems say something along the lines of simplify or solve. We have one that says factor. Remember, in algebra, we learn how to solve equations. You don't simplify equations, you simplify expressions. This is an expression. Down here we have some equations. I would like to do, I think, just 2 problems from this section. In fact, I am going to focus on number 6 and number 7. Okay. Now, both of these are equations. We want to solve each one. One of them involves exponential functions, and the other one involves logarithms. And it's really, really important in calculus that you have a good handle on all of your prerequisite material. Algebra, you kind of are expected to have on lockdown coming into this class. In fact, let me take a second to sort of illustrate sort of what we're doing in calculus as far as this prerequisite material is concerned. I like to say that in calculus, it's really the first time your mathematical training wheels are being removed. You're kind of expected to do a lot of algebra and arithmetic and stuff like that without having to put a huge amount of effort into it. So, for example, if I was in an Algebra 1 class, Algebra 1, and I gave you a problem like this, solve 3x minus 1 equals 10, okay? In Algebra 1, typically the way that you work through a problem like this is you show every single little step. So the Algebra 1 students will say, first I add 1 to both sides, and then they write the solution to that, 3x. They might even show that this gets canceled out here, equals 11. And then we show that we do we divide by 3 on both sides. And then you might even show that this cancels out and I get a solution of x equals 11 thirds, something like that. That's how this problem would look in an Algebra 1 course. By the time you are in calculus, you should be able to look at an equation like this and say, yep, 3x minus 1 equals 10. spend a couple of seconds looking at it, I can see right away the answer is x equals 11/3. You need to have that kind of a handle on algebra. Not saying that you shouldn't do any steps. There's plenty more complicated problems where you should be showing some steps, but this is way too much for a calculus class. This is what you're doing when you have what I call training wheels. You're learning algebra. You have to write out all of these steps to kind of get a feel for what's going on. But by the time you are here, you should be able to know within a few seconds that this is the answer to this. Okay, and the reason for that is, in calculus, there is a whole lot of algebra in the problems that we're doing, and you do not have the time to do all of this. Okay, the problems are much longer, much more involved than what you've been doing previously. So that's my little, I don't know, rant, I guess. Not really a rant, my little disclaimer. So now that we've covered that, let's go back into this algebra stuff here. I have a couple of equations that I want to solve. I'll just use this page here. So this was in section A. I'm going to call this problem A6. Okay, section A, problem number 6. We want to solve e to the 2x plus 3e to the x minus 10 equals 0. E to the 2x plus 3e to the x minus 10 equals 0. Okay. Now, you've probably done plenty of equations like this in algebra or pre-calculus or whatever course you took that covered this. And really what we're looking at is a quadratic equation in disguise. Notice, first of all, the e to the 2x here. Using my exponent properties, this can be written as e to the x squared plus 3e to the x minus 10 equals 0. And now we do something that's going to be very, very useful in calculus. We're going to make something called a variable substitution. So what I'm going to do is define a new variable. I'm going to call my variable u, and I'm going to set it equal to e to the x. And what that does is it allows me to go back into this equation, and anywhere I see an e to the x showing up, I can replace that with a u. So this e to the x becomes u, and I get a u squared in my first term. U squared plus 3, this will become u. 3u minus 10 equals 0. I don't know why I wrote 10 there. Equals 0. Okay. Now, I see a quadratic equation, and these we've had lots and lots of practice solving. We have different options available to us. We could use the quadratic formula or something like that. In this case, I think it makes sense to try factoring. Without too much trouble, you should be able to see that this expression factors to u plus 5, u minus 2. Okay, u plus 5 times u minus 2 equals 0. And at this point, now that I've done this factoring, this is where I can take my u's and substitute back that e to the x that they're defined to be equal to. E to the x plus 5 times e to the x minus 2 equals 0. Okay? And at this point, we know that this implies, using our zero product property, that e to the x plus 5 equals 0, or e to the x minus 2 equals 0. Or equivalently, e to the x equals negative 5, or e to the x equals 2. Now, you should know, and this is where it's really important to have a good conceptual grasp on what you're doing. In algebra, we do so much practice with solving equations that they become a little too mechanical, and we don't ever really stop to think if what we're doing makes sense. And here's what I mean by that. If you were thinking too mechanically, you would try to solve each of these separately, and you would say, okay, I know how to solve an exponential equation. I need to take the natural log of both sides. So I could say here, x equals the natural log of negative 5, x equals the natural log of 2. However, the natural log of negative 5 is undefined. The natural logarithm is only defined for positive real numbers. So this doesn't give me any solutions. Another way of saying that is that the exponential function only ever equals positive numbers. So if I get something like this, it's not contributing anything to my solution. This implies, if I were to solve this one, that my solution is x equals the natural log of 2. Okay? So that's going to be my solution for number 6 here. Now, I do want to point something out as well. And this is something you've probably already picked up on in pre-calculus and what have you. More often than not, we're not going to plug something like this into a calculator. We want to leave answers most of the time in their exact form. And the natural log of 2 is an irrational number. It's going to give me a non-terminating decimal that doesn't have any repeating pattern. We want to avoid that most of the time. Now, there are cases where we would want to plug this into a calculator, and usually it'll be kind of clear from the context of the problem when we want to do that. But more often than not, I leave things in logarithm form, radical form, unless they simplify very nicely. Okay, so that was problem number 6 from our algebra section. Let's take a look at the second problem in there, which was here. Logarithm equation, or logarithmic equation. I want to solve log of x plus log of x minus 1 minus 1. Now, one thing to remember here is that logarithms, if you don't see a base written here, if it just says log, the assumption is that the base is 10. And it's important to remind people of that because if you major in engineering or some related fields, sometimes in those fields they use the notation log here to actually mean the natural logarithm. So in those sorts of courses, you might look at this and think that's log with a base of e. But in math, typically we define this to be log base 10. So we need to remember that for this problem. Okay, so I'm going to go like this. Let's do number 7, A7. Okay, the problem here is log of x plus log of x minus 1 equals 1. Okay? Now, in a problem like this, what we would want to do is begin by combining the logarithms using our known logarithm properties. So when I have a sum of 2 logs where the base is the same in each one, I can combine them into a single log where I multiply their arguments, x times x minus 1. So this is the same thing as the log of x times x minus 1 equals 1. Okay? And what I want to do now is take this logarithm and put it into exponential form. So the literal meaning of this is that 10 to the first power equals x times x minus 1. 10 to the first power equals x times x minus 1. Okay? And I can see now that this will also turn into a quadratic equation. So I would multiply the x through, subtract this 10 over. I'm going to get 0 equals x squared minus x minus 10 as a solution to this. Okay? Now, in the previous example, we also had a quadratic equation after making a variable substitution, and we were able to factor it fairly easily. In this case, this guy is not factorable, but we can still solve it using the quadratic formula. So I'm going to use the quadratic formula next. X is equal to negative b, which would be 1, plus or minus the square root of b squared, that's negative 1 squared, minus 4ac, 4 times 1 times negative 10, all over 2a, 2 times 1. Here we have x is equal to 1 plus or minus. Here this is equal to the square root of 41, if I do the arithmetic there, over 2. Okay. Now, once again, we don't want to be too mechanical in how we approach a problem like this. We need to make sure that our answers make sense. And again, it's very, very easy to jump into a problem of this nature, get a solution, and say, I'm done, right? But with logarithms, we have domain restrictions that we have to keep in mind. Logarithms are not defined for all real numbers. In particular, you cannot plug a negative number. In fact, you can't even plug 0 into a logarithm. That's undefined. And looking at my solution here, One of these two solutions, 1 minus the square root of 41, for example, over 2, is a negative number, and it's fairly easy to see that. So even though this is giving me two apparent solutions, one of them has to be thrown out. So I'm going to say 1 minus root 41 over 2 is negative. So we can't use it. That means that the only actual solution that does work is 1 plus the square root of 41 over 2. That's a positive number, and even if I were to plug it in here where I plug in it in for x and then subtract 1, I would still have a positive number. You can verify that yourself. It's very easy to do that. There's no problems there. And so for number 7, we have just the single solution. Okay? Awesome. So there's more algebra problems, obviously. I just wanted to do those two, but make sure that you've tried all the others as well. Let's move on to these geometry problems, okay? So this is geometry and analytic geometry. Analytic geometry is doing geometry in the coordinate plane, essentially. So we're working with coordinates, whereas just regular old Euclidean geometry doesn't necessarily have a coordinate system superimposed over the things you're working with. You'll notice there's a few different problems here, and some of them have different parts. So for example, number 1, it's saying without sketching the graph by hand or by using a graphing utility, describe the graphs of the following. Okay, so for these, the purpose is to be able to take a look at an equation in two variables and be able to recognize what its graph looks like without having to plug numbers in for x and get corresponding values for y. By the time you're in calculus, you need to have a really, really strong grasp on what the graphs of certain common functions look like. So for example, you should be able to look at this and right away say, that is the equation of a line. I can see that it has a slope of negative 2/3 and a y-intercept of negative 1.5. You should know that without having to think really hard about it. Let me skip down to C because I want to talk about B in more depth. C, so taking a look at this, right away I could tell you this is a parabola. Because I can see that we're dealing with a quadratic equation. And a quadratic equation in two variables of this particular form would produce a parabola. But what else can I say about that parabola? Well, for one thing, I can tell you that it's a downward opening parabola because the leading coefficient would be negative. I see a minus out here. In addition to that, if I compare this, so I'm going to say compare to y equals negative x squared. We would think of that as like a parent function for the parabola, but this one opens downward because of the minus out here. How does this parent function, this simpler equation, compare to this one? Well, we have translations that are occurring here. We talk about transformations of functions, which are things that affect the graph of a function in a specific way. So when this x minus 1 here implies that this graph, this parabola, compares to this one in the sense that this is shifted 1 unit to the right. The plus 2 out here indicates that this parabola has been shifted 2 units up. So you see how I'm describing a comparison between an easier to manage graph or curve to get an idea of what this one looks like. Now how about this guy right here, y equals 25 minus x squared. Under a radical, so square root of 25 minus x squared. For this one, you may not know right off the top of your head what this looks like, but I guarantee you by the time you get through Calculus 1 and even Calculus 2, you'll be able to look at that and know exactly what it is, because this is a common graph that we see. You actually see these kinds of equations a lot in Calculus 2. This is the graph of a semicircle. And how do I know that? Well, if I were to manipulate this equation a little bit, if I were to square both sides, y squared equals 25 minus x squared, and then if I were to say, if I add the x squared over, x squared plus y squared equals 25, I know that this is the equation of a circle. centered at the origin with a radius of 5, because this is r squared over here. But I said back here that this is a semicircle, not an entire circle. So why is this one not the entire circle? Well, if I were to reverse these steps, if I were to solve for y again, so subtract x squared from both sides to get here, take the square root of both sides to get here, anytime you take the square root of both sides of an equation, you're supposed to be getting a plus or minus right here. And I don't have that. In fact, the square root function cannot produce negative numbers by itself. So this will only give me non-negative values of y. That means that the equation of this thing will never go below the x-axis, because that's where negative y values live. Instead, we're looking at a semicircle centered at the origin still with a radius of 5, but it lies above the x-axis. That's what that graph would look like. Okay? It's important that you're comfortable knowing that. Let's take a look at number 2. So here we're given 3 more equations, and we're being asked questions about the graphs of these equations. And we are not going as far as graphing them entirely by hand. We're really just asking, where are the x and y intercepts of these graphs? So for this, it's important to know how to come up with an x or a y intercept for a graph when you're given a function to work with, or given an equation to work with. If you remember, in order to find the x-intercept of a graph, the x-intercepts are where the curve crosses the x-axis, but those only occur when y is equal to 0. So if I want to find the x-intercept of a graph of one of these equations, then I'm plugging a 0 in for y and solving for x. Similarly, if I want to find y-intercepts for the graph of one of these equations here, then I would plug a 0 in for x and then solve for y. So let's just do one of these. Let's say, let's do C down here, okay? So this is problem BC, or B2C, because it's section B, problem 2, part C. We're given this function, y equals, let's go like right there, x squared minus 1 over 3x squared plus 4x plus 1. Okay, and I need to find the x and the y-intercepts. So let's start with my x-intercepts. To find the x-intercepts of a curve for a given equation, we plug 0 in for y. So that means I would put 0 in for the y there, equals x squared minus 1 over 3x squared plus 4x plus 1. And then I try and solve this. If I multiply both sides by that denominator, I get 0 equals x squared minus 1. And you should be able to tell that the solutions to this are x equals plus or minus 1. Okay, you can do that by factoring, you can do it by isolating x, but that's an easy one to solve. Now, x is equal to plus or minus 1. Those are not my x-intercepts, because intercepts are points, and these are just numbers. So what these represent are the x-coordinates of my x-intercepts. But my actual x-intercepts would be 1, 0, and negative 1, 0. Or I can write that this way, plus or minus 1, 0. Those are my x-intercepts. What about the y-intercepts? For my y-intercepts, I do the opposite. I plug 0 in for x. So that's 0 squared minus 1 over 3 times 0 squared plus 4 times 0 plus 1. Okay? And this, very easy to see, would just equal negative 1. So my y-intercept is 0, negative 1. Okay? One important thing to note also, when you're looking at the graph of a function, and this is the graph of a function, you can only ever have, at most, one y-intercept. You should never have more than one. And if you think about why that's the case, if you had more than one y-intercept, then the graph of that function, or that equation, would fail the vertical line test, meaning it's not a function. Okay, so you should only expect to see one, if any, y-intercept in a problem like this. Okay, so we've done that. Let's keep going. I'm going to skip the inequalities for now. I'm going to let you work on those. Again, all the answers are in the back. This one, let's see, that's kind of a basic trig. I think I want to skip that one too. Okay, here's a good one. So number five in our geometry and analytic geometry involves the distance between 2 points occurring on two different functions. So we're given two quadratic functions, f of x equals x squared plus 4, and g of x equals negative x squared plus 6x minus 8. And what we're asked to do is to come up with some function that we're going to call d of x, which represents the distance between x f of x. Notice this would be a point on this parabola here, and x g of x. This would be a point on this parabola here. And it's important to notice that both of these functions are using the same x value. Okay? Now, one way to approach this is to try and use distance formula, which you learn in geometry. You cover it again in Algebra 2. It's a really important formula to know. But I'm just going to tell you distance formula is more complicated than this needs to be. So instead, let's start by thinking a little bit about what the graphs of these equations would look like. So this is B5. Okay, I have two functions. F of x equals x squared plus 4. G of x equals negative x squared minus 6x minus 8. So negative x squared plus 6x minus 8. Okay, now what I'm going to do is think about the graphs of these things, because the question concerns points on the graph of these functions. And I'm not going to bother spending the time to get a super accurate graph because it's unnecessary for what we're doing here. Instead, though, I just want to try and get a quick, rough sketch. So for example, the function x squared plus 4, this would look like the parabola y equals x squared shifted up 4 units. That means its vertex is going to be right here at the point 0, 4. And because I have a positive leading coefficient, this parabola will open upwards. Like that, okay? Now this parabola, the one corresponding to g of x, is going to open downwards because it has a negative leading coefficient. And if I wanted to determine what the vertex of this parabola was, we have a little formula for that. The vertex involves the quantity negative b, let me write it this way, vertex, negative b over 2a, and then I would also plug in g of negative b over 2a. Okay, what is negative b over 2a in this case? Well, negative b is negative 6. 2a is equal to negative 2 times 1. So this is equal to negative 6 over negative 2. Okay, simplifying that down, this is going to give me 3 here. And then to determine what I would get here, I would plug 3 in to this function. Okay, so what is that going to be? If I plug a 3 into this, negative x squared. 3 squared, that would be 9. 9 minus 8, that would be negative 17. Right? Negative 9 minus 8 is negative 17. If I plug a 3 in here, 6 times 3 is 18. Negative 17 plus 18 would be 1. So that tells me that the vertex for this parabola is at 3, 1 here. And that, because this is a downward opening parabola, that vertex represents the highest point on that parabola. Okay? Now, why did I bother with these graphs? Well, again, the problem that we're trying to solve is that for any given value of x, I want to find the distance between the points x, g of x, and x f of x. And in order to find that distance, because it's vertical, the distance between these two points here are really just going to be the difference between the y coordinates of these points. And that's strictly because this is a vertical distance. No matter where I choose this x, it's going to be a vertical distance in each case. So really I just need to subtract my y coordinates. But the reason I wanted to graph these parabolas is because distance should be a positive number or 0. It can't be negative though. In order to make sure I'm doing the difference in the right order, I should know which point has the larger y coordinate and then subtract the smaller y coordinate from that. From this, I can see that no matter where I choose my x, the point on the graph of f of x will always be above the corresponding point on the graph of g of x. So that means my function d of x should be of the form f of x minus g of x. That would be the difference between these y coordinates in the correct order. Of course, this would just look like f of x, which is x squared minus 4, minus g of x. Now you have to remember to put parentheses around this. And this is going to be a common mistake. I'm going to bring this up again. When you're subtracting an expression that has multiple terms, you need to put brackets or parentheses around it. Otherwise, you're going to end up only subtracting the first term. Negative x squared plus 6x minus 8. And this gives me d of x equals, after simplifying this, 2x squared minus 6x plus 4. That would be the end result there. Okay, I'm just going to compare that to my answer key real quick, make sure I didn't make any mistakes. And where are you? Yes. Or no, no, I'm sorry. No, that's correct. Okay, so that's it for this video. We're going to do some more problems, but we'll make a part 2 to this.